Alright, ladies and gentlemen, welcome back. So we're going to continue with looking at questions on what we learned on work energy, power and potential. So in this session we're going to look at something on conservative force fields. So I'll open the document again. Okay, so this was the part talking about conservative force fields. This is conservative force fields, and here we're saying that suppose there exists a scalar function v such that f is equal to minus grad v. This is a statement which shows whether a force field is conservative. This function must exist. Okay, a function v must exist such that f is equal to minus grad v. Okay, and here I'm going to show you what this operator is. I'll show you what this operator is in the example that we're going to do next. And the other condition was that this del operator cross f, which can be read as KF, must be equal to 0. Okay, so the K of f must be equal to 0. If we can prove this, then we've shown that a force field is conservative. And let's look at this example. So you see here we have number 7. Let's look at number 7 here. Number 7 is saying show that f1 equals minus 2xi minus 2yj minus 2zk is conservative. That's what we've been told to show. We've been told to show that this force field is conservative. Okay, and for us to show this that f1 is conservative, we're going to follow the procedure here. So you see I've just written f1 here, which is this, and to show that it is conservative we must show that the K of this force field must be 0, which is the del operator cross f. Now this del operator, which I've been talking about for some time, it is just this. Del is just partial over partial xi plus partial over partial yj plus partial over partial zk. Okay, so this operator operates on a quantity which we've been given, and as you can see it's a vector. This is a vector because it's having a basis vector which is I, a basis vector j, a basis vector k. So this is a vector. Now how do we take the cross product? We follow the same procedure. If you've been given two vectors and you're told to take the cross product, you just say find using the determinant method. We use the determinant method where we place I here, j here and k here. After that we place this component which is partial over partial x here, partial over partial y here, partial over partial z here. Okay, and then you take minus 2x, you put it here, minus 2y, you put it here, minus 2z, you put it here, in order as they should be. So all components having I are in this column, all components having j are in this column, and all components having k are in this column. Okay, and then from here use the same determinant method of taking cross product. So here we say we take I, we put it outside, we like cover this part and this part, and then multiply this times this and this times this. You remember the method of taking determinants. This is what we're just doing. We take I outside and then we take partial over partial y. Okay, I outside, then we multiply this times this, we get this. This times this, we get this. You see, minus this times this, we get this. Okay, then the next part which follows should have a minus, which you say minus j hat. Okay, coming from this j, so we say minus j hat open brackets. So now since we're on J, we cover this and this, so we're going to multiply this times this minus this times this. So when we do that, we'll get this quantity minus this quantity plus k hat, which is that. So now we're on this k hat here, so we'll cover this and cover this, so that we multiply this times this minus this times this. Okay, this is the procedure we use. I'm sure you all remember how to find the cross product of a vector of two vectors using determinant method. This is how it is done. Okay, and okay, we get that. This is how we do determinants. We've all done matrices here, so we know how to get the determinant, so we use the determinant method here. So when you do this part, you arrive at this operation and this operation and this operation. So now here, when you look at this, you see that this operator is differentiating partially with y, but what function do we have in parentheses? This function is depending on z. Okay, we're differentiating with respect to y, partial with y. Okay, so we're differentiating partial with y, but this function only has a z, right? So if that is the case, then what we'll have is a 0 here, because this function here inside, this part inside, will be treated as a constant. Why is it treated as a constant? Because we're differentiating with respect to y, but it has a z here, so it will treat it as a constant, since we only want something partially with y, minus partial over partial z. So here it's partial with z, but here we have what? We have a y, so this thing will be treated as a constant. Okay, because it's different from what we are differentiating with respect to, yet with partially with y. If we do that, this thing will become 0. Same applies here. When we differentiate this, it will become 0, because we are differentiating partial with x, and this one has a z, and this one minus partial over partial z. Here we're differentiating partial with a z, but it has a x. This function inside has a x. So this will continue, we'll keep on getting zeros here. Here we'll have 0, here we'll have 0. So we get 0, 0, 0, which is this 0 plus 0 plus 0, which gives 0, and we get a 0 vector. So by proving this, we have shown that this force field is conservative. Alright, we've just shown that this force field is conservative. Alright, and there's also another question. There's question 14 here, which is saying show that f, which is equal to 2xy plus 2z cubed I plus x squared j plus 3xz squared k is a conservative force field. We have been told to show that this is a conservative force field. Okay, so we follow the same procedure which we did last time. We just take del cross f, this f, and we find that it is if we find that it is equal to 0, then we have shown what we wanted to show. So as you can see here, I said that when we look at number 14, yeah, I said answer yourself, because we follow the same operation which we are just from doing. We follow the same operation which we are just from doing, so this you can answer yourself. Okay, luckily this question part A is independent of the second part and the other parts. So from question 14 we'll start looking from part B. So part B here is saying find the potential. We want to find the potential from this force field. since we've shown, after showing that it is conservative here, we can find a potential. You remember the definition for a conservative force field? Let me just show you something back here. One of the definitions, it had how many definitions? It had 3. There was this, there was this, and there was this. All these are theorems proving that something is conservative. So the first definition was that there should exist a potential V. Okay, there should exist a potential V, a scalar function V, which is a potential such that F is equal to minus del V. Okay, now just this function here, it's the one we're going to work with. Here, when you look at it, I've placed it here. F is equal to minus del V. So we've been told to find the potential. We have this force, we have the del operator, but we don't have the potential, right? We have this force in the question. The del operator, it is known and fixed, it is standard, but we don't have V. Alright, so using this equation, we'll plug in what we have, right? We'll plug in F, which is this, must be equal to minus del V. So minus del V is just this del can multiply throughout inside, this V, this potential V, it can multiply throughout this operator del, and when you multiply this V, when you multiply this potential V here by this operator, you get this kind of operation. You remember there's a negative there, you get this kind of operation, minus partial V over partial xi minus partial V over partial yj, and minus, this is a minus, partial V over partial zk. You get this operation. Okay, this is something you get, and when you get this, you must equate each of the parts together, right? Since this part is equal to this part, so here you equate minus partial V over partial x to this part here with the I. So this part has got the I, and this part has got the I. You equate them together. Okay, so when you equate them, you neglect these i's because you're only interested in the potential. So you get this minus partial V over partial x to xy plus z cubed, right? When you equate this to this, and then we're also going to equate this to this, and then we'll equate this to this. Alright, so starting with equating this to this, we'll have this equation here, and from this equation here, we can solve this. This is something like a differential equation. We can solve it by first by integration methods. We can multiply throughout by partial over partial x. So when this partial x goes to the right here, right, it goes to the right there, it can become dx. So you can write it as dx there. Okay, we can say dx, and this negative, you can divide it throughout, you get this part on the right. Okay, and then integrating here, introducing an integration symbol or sign, and here also introducing an integration symbol. Alright, since you just want the V, you aren't interested in the V here, so you can multiply this partial x by this thing to get this, then you integrate throughout. So here there was missing an integral sign here. There should be an integral sign there. So when you integrate this, you just get V. This integral will vanish with this partial sign, and we just get V equals minus 2x squared over 2y minus z cubed x plus a constant c. So after integration, we'll get this. Alright, we'll get this kind of expression, and then simplifying this expression we get this. Okay, so we'll call this equation 1. After getting this equation 1, we also get now this part in the y will equate to this, right? We equate to this, and then we do the same process as we did on the first part here. So now this other part, when we equate this to this, we're getting this, which is minus partial v over partial y being equal to x squared. That's what we're getting. And then multiplying this partial y with this, we'll get something like this. Okay, this is the integral of minus partial v being equal to the integral of x squared y, the integral of x squared partial y. Alright, now when you look at this, right, here what is happening is that this integral sign is cancelling with this partial d, okay, and we're just getting v here, and the negative here we're dividing through by a negative. Here divide by the negative, it will vanish, and here dividing by the negative, this thing will get the negative. And this thing here is an x. Well, here we have x squared, but we're integrating with partial y, mean that this x squared will remain like a constant, and then this part will get a y, right, like this. So this will get an answer here, plus another constant c1. So this is our second equation, and finally we equate this part with a k with this part with a k, and we get this kind of operation. So dividing through by negative and multiplying partial z with this part on the right, like cross multiplying, there's nothing special happening here. We get partial, we're just solving for v here, we're trying to solve this equation for v. Alright, so we get partial v being equal to the integral of minus 3x z squared partial z. Alright, then we take the integral there and the integral there, cancel there and cancel there, we get v being equal to minus 3x z cubed over 3 plus c2, where we have v equals minus xz cubed plus c2. So we get this v here. C is just a constant here, there's nothing special. C2 constant, even the other c's were constants. Okay, now to get our common potential, we must get all the different parts of potential. As you can see here, we have minus x squared y and minus z 3x. So now let's start with the minus x squared y, we get it, and the minus z cubed x, we get it. These are different, this thing is different from this, so we get these as they are. And since this is v and this is v, they are all potentials, we should have some common potential. Now when you look at this other v in equation 2, it also has minus x squared y, it also has minus x squared y. So here we don't get another minus x squared y, and this other equation 3, it has minus xz cubed, so it's already existing in what we took first. So our common potential will just be minus x squared y and minus z cubed x. That will be our common potential. By inspection, the common potential should be this. So for us to get the common potential, we must just pick out all the terms which are distinct, all the terms from these potentials which are different, pick them out and then write them in full. like that. So this will be our full potential. Here we have that, so we write it, and we have the minus x squared minus x z cubed, which is this x z cubed. Remember, there's a minus outside there, so that is what we have. And there's part C, which is telling us to find the work done in moving an object in this field from 1, minus 2, 1. You are just saying find the work done in moving an object in this field from 1, negative 2, 1 to a point 3, 1, 4. So I'm moving from this point to this point. Now we want to find the work done. Now if you can remember the formula for work done was also defined as V1 minus V2, meaning potential at 1 minus potential at 2. Okay, if that is the case, we have the potential here, right? We have found the potential here, which is this function. Now taking this potential, we plug in our coordinates which we've been given. We plug in at 1, we get this operation. We've been given here our coordinates. We've been given 1, negative 2, 1. This is at 1. Potential, initial coordinate here, and the final coordinate here. So we first start with the initial coordinate, which is 1, negative 2, 1. When we plug in those values for x, y, and z in here, we're getting this. Okay, and we're getting a 1 for V1, and for V2 we take these coordinates. Okay, for V2 we take these coordinates at point 2 and plug in here, and we get V2. When we plug in here, you get V2 to be this. You get V2 to be that, and you have V2 being equal to minus 2, 0, 1. So now when you say V1 minus V2, you get 202 as your answer. So your answer here will be 202. Okay, your answer will be 202. So that is your work. Alright, that was it for this session, and I'll see you again. Alright, so have a good time. I hope you'll be able to understand some of these things, and I'll see you in the next sessions which we'll do. Alright, bye.